Thanks, Pio. So like he said, my name is Preston Sandusky from Kestrel Bikes, and also have John St. Dennis, also known as JD, with me here. I have quite a few slides, so I'm actually going to try to go through them pretty quickly, but my background, currently I'm the product and managing director at Kestrel. I started out as an engineering manager, and I actually was president for a while there before we switched some ownership around. So my basic background is mechanical engineer, U.S. Air Force, aerospace, carbon fiber stuff. And we're really happy to have the opportunity to come here today because Kestrel's a Northern California company, and Kestrel made the first all-carbon fiber bike in the world on a production for sale basis. And the technology and the engineering to do that came out of the Bay Area and the Sacramento area aerospace industry. You know, back before companies like this were so prevalent here, the aerospace was really huge down here, and a lot of that early technology spun out of that. So let me just get started. Like I said, I am going to go through some of these pretty fast. Just want to give a brief history of when Kestrel started. We kind of already talked about it. And then we'll talk a little bit about the materials capabilities and why we use carbon fiber. And then kind of walk you through the basic steps of the design and development cycle on one of our products, or a couple of our products actually. So like we've already said, Kestrel started in 1986 down in Santa Cruz. And what happened is the guys who had started Trek bicycles about 10, 12 years prior to that got together with aerospace carbon guys and decided to make a full carbon fiber bike. Prior to that, there were bike frames made with carbon tubes, typically glued to aluminum lugs. Even steel lugs early on, but at the time the Kestrel came out, carbon bike was round carbon tubes bonded or glued to aluminum lugs. So it was very much metal bicycle technology with just the tubes replaced by carbon. So the first Kestrel was called the 4000, or the Model 4000. Here it is here. I keep looking at the screen, but it's actually in front of my face. And this bike revolutionized cycling in a lot of ways, actually. I mean, the obvious thing is it was the first full carbon fiber composite molded bicycle frame. But it also had things like, it was the first production frame with aerodynamic tubing. So, and I'll talk a little bit more about that when we get into it, but the beauty of carbon fiber is its moldability, and you can shape it however you want. We try to shape it in ways that make sense, but it's basically, it's just infinite what you can do with carbon in a molded shape. Once the first road bike came out, we turned our attention to mountain bikes and triathlon bikes. So in 1988, we came out with actually a full suspension bike prototype. And many people regard it as kind of the bike that helped kickstart the full suspension craze that is now commonplace. More people ride suspension bikes than non-suspension now. And then as a result of that bike, this is it here, the Nitro show bike. It was actually a collaboration. For those of you who kind of know some of the bike history or some of the bike names, it was a collaboration with Keith Bontrager from Bontrager Cycles, Paul Turner, who ended up starting RockShox, which of course was in about 88, 89, just was pioneering the suspension fork for mountain bikes. And of course, Kestrel with the carbon fiber side. We didn't end up making this bike. We ended up making what we call a hardtail version, which is actually a very similar design, but without the rear suspension, because the things like the brakes and the shocks didn't actually exist in the market at the time, and it was pretty. This bike was pegged at about $6,000 in 1998 for a mountain bike. Later on, some of the other things we brought in that we kind of pioneered to the bike market, the EMS fork, or the carbon fiber road bike fork, was a huge thing. Came out in 1989, and we also made the first all-carbon triathlon bike. So triathlon is a sport that's pretty big these days and really growing fast. And at that time, it was really in its infancies. I think we were maybe the second company to make a tri-geometry specific production bike, and the first one to apply carbon and aerodynamic tubing to a triathlon or time trial bike for production. We also came out with this bike in about 1992. This is a 500 SCI. I think the photo's a 500 EMS, but the 500 SCI was its predecessor. And as you can see, it has no seat tube. And this is a really good example of what carbon fiber can do, not just for bicycles, but in any structural design. Because there's just no way you were going to take steel or aluminum or titanium metal bicycle frame material and have any kind of efficient structure by removing a tube like that. And what this bike did, this was actually a road bike, but it was used by a lot of triathletes as well, as you can see by the setup in this photo. But what it really opened the door for was some aerodynamic freedom with our triathlon bike designs. And you'll see some more of that in the, when I get to the design process. This is a lot of words here, but basically the materials that we use to make frames, it comes straight out of aerospace, military and aerospace industries. So it's called carbon fiber prepreg. The prepreg means that the fibers are typically aligned along an axis and then coated or treated with a matrix material like epoxy resin. So prepreg means pre-impregnated with, in our case, the epoxy resin. I mean, literally, we were taking engineering material specs right out of aerospace and applying them to these bikes. And in fact, probably the most important thing that Kestrel pioneered back in the day was the marriage of real engineering to the bicycle industry. Prior to that, nothing against those engineers, but actually a lot of the bike companies had engineering departments that didn't have engineers because it's mostly just drawing tubes and mitering drawings to see how what the tube lengths are and how they come together to be brazed or welded. So this was a very engineering intense project, and I can tell you that joining Kestrel in October '87 and going from the Air Force Composites office and the aerospace side, and then watching them lay up a whole bicycle frame in one piece with this material, it's the kind of thing where a trained aerospace engineer would just say, initially just say, you can't do that, you know, it doesn't work. But bicycle guys are pretty inventive guys, you know. I mean, you're talking about people like the Wright brothers, and so there's people that tend to have some ideas or some dreams and go after it and not worry about what other people say can or can't be done. And I'm sure you folks here are familiar with that as well. So why carbon fiber? The best thing about carbon fiber in a bike frame is the stiffness to weight ratio. Bicycle frames are what we call stiffness critical structures. So as many of you know, you get on a bike and you don't want it to be flopping and flexing around, you want it to be stiff. But it's a two-dimensional structure. The rear end is a little bit triangulated in the third dimension, but that main frame and that main power transfer is done in a two-dimensional plane. So stiffness becomes really the issue in a bike frame and a lot of bike components. Strength is too, but with metals, you sometimes have the condition where you have to design something around the strength of the material rather than the stiffness. With carbon, because the stiffness is so high, Usually once you have the stiffness under control, the strength almost comes along with it, with the design. We do have to beef up areas for impact or certain really high-stressed areas in terms of strength or structural testing, but stiffness is the key. And carbon fiber composites far outweigh metals, and I have a little chart on that. Excuse me. So here's a stiffness comparison. Specific stiffness, I didn't really ask how many of you folks are engineers or material people. Specific stiffness means stiffness to weight. And you can see, I don't really have a pointer, I think, but so you can see here, down here, the little blue bars, these are the typical frame building metals. Steel, aluminum, titanium. Those are the metals that were being used when Kestrel came out, and they're still the metals that are being used in frames today. Maybe not so much as they used to be, because carbon is probably the dominant high-performance material in bike frames now. But as you can see, those metals have actually different stiffness properties and capabilities, but when you factor in the density of the metals, that their stiffness to weight comes out very much the same as each other. And also with stiffness, it's pretty much regardless of the alloy of the metal. With strength varies more with the alloy, but stiffness to weight is pretty much the same. And then you can see on the far side the type of carbon materials that we use. Here, I don't know if I can be here without being in the way or off the camera. This is the 700K material, or our quote-unquote standard material. And then the 800K here is our higher modulus material, or what we use on our SL frames. And you can see the specific, I don't know if you guys can quite read the numbers, but you can tell from the graph that the specific stiffness of carbon fiber that we use in the frames is about 5 to 7 times the stiffness to weight of the metal frame material. So from a pure engineering standpoint, if you don't have a background in the traditional frame materials and you just look at materials available, it's just really obvious to us that carbon fiber composite materials are the way to go. The little red bars next to the carbon is actually the carbon epoxy. Carbon, you can't build a bike just with carbon. The epoxy has to hold it together. So when you factor in about 35 or 40% epoxy, but you still have a stiffness to weight ratio of about 3 to 4 times what the metals have, and actually more than that with some of the newer fibers. Strength to weight is the same thing. There's a little more variance in the metal materials, depending on the alloys, but they're heavy. Carbon fiber epoxy, again, as you can see, it has even higher strength to weight than stiffness to weight, and that's why I said if you make the frame stiff enough, the weight's almost, or the strength is almost always already there for you. So again, the fibers themselves that we use, 11, 12, 13 times the stiffness to, or the strength to weight or specific strength of the metal materials, and then the carbon epoxy blend is still going to be 6, 7, 8 times the strength to weight. It's an engineer's dream. A couple other things that weren't on the slide. The other big thing, the main point there, I think, is the big one, that carbon fiber epoxy composites are fiber reinforced plastic. So the epoxy matrix is surrounding all those fibers, and it's plastic basically. So the shock damping capabilities of a carbon composite material is 10 to 15 times the shock damping of metals, of these traditional frame metals. So imagine if you had a steel bell, an aluminum bell, and a titanium bell. They would all ring. You hit them, they would ring. You make a carbon epoxy bell, and it's like hitting a plastic bell. So it just doesn't ring. What that allows us to do is separate the ride quality and the damping of the frame or the structure from the stiffness and the strength and the performance side of it. So if you make, let's say you make a titanium frame, you want it to be reasonably light and you want it to be comfortable. Well, if you make it very stiff, it won't necessarily be so comfortable. If you make it comfortable, you're getting the comfort out of flex. Flex is bad in a bicycle frame. So there's that balance with metals. You try to balance it out. And I defy anybody to make a non-suspended frame out of metals that is as stiff as a carbon frame and still has the kind of comfort you're looking for. So with carbon fiber, you make that structure, you say, I want it this stiff, it has to pass these strength tests. Blend or vary the fibers and the design according to the weight you're looking to get. And the shock damping is separate from those properties. So all of a sudden you have a super stiff bike like, like these up here, the little one over there, and very stiff, very, very efficient, and yet really smooth frames. Now, if you go up against a curb or something, it's a stiff frame, you're going to feel it. But that rough road buzz and smaller potholes and cracks and things in the road, it just gets rid of those. You don't get that bite through the handlebars and that ringing in the frame. So, a couple general features or general design approach in pretty much all of our frames and products using carbon. And by the way, we only make carbon products. The first one is a modular monocoque construction. And the frame, actually these are the solid models for the various sizes of that frame, the Talon frame down at the end. But way back when, we used to try to mold these frames all out of one piece, and it was great. It worked great, but it was very complex, very expensive, and very much less repeatable. So about 10 years ago or so, we've kind of gone to this modular monocoque construction, and what that is taking all the best out of the carbon fiber design, but breaking it up into not a lot of pieces, but just a couple main structures. And for instance, the main frame here. So that's a solid model that the mold or the tooling is made from, but it shows that the whole main frame is molded in one piece. And then after the talk, you folks can get a better look at the bikes up here, and you can actually see where, say, the seat stay assembly in the rear is one piece, and then the chainstay and assembly in the rear is one piece, and then they're all put in a bonding fixture and locked permanently together. The other thing that's a really big part of our design work, and I think that the thing that carbon leaves you wide open to opportunity, is in optimizing the tube shapes and the junction design. So it's somewhat doable in metals, but difficult. Usually there's round tubes or near round tubes. But in carbon, and if you look at some of these designs, you'll see that from one end of a tube to another, it can be a completely different section. It's all designed around the load conditions and the structural requirements at any given point in the frame. So also we can bring in aerodynamics. You see the aerodynamic tube shape there in the down tube. Maybe the down tube might flare out to the bottom bracket to make it stiff there. Some of the sections go from flat at the front at the head tube of, say on the top tube on the top of the bike, up near the front at the head tube, they might be more of a vertical section and kind of gradually morph to a more horizontal section, gradually morph to a vertical section. So it's infinite. It's anything you can put in the computer, which is pretty much anything these days. Didn't used to be. Pretty much anything you put in there, you can make with carbon fiber. The size-specific structural design and fiber layup, again, it's becoming a norm now in a bike frame with carbon fiber, whereas with metals, you might be able to use a thicker tube or a bigger diameter tube as you went up in size, but typically it was really hard to have a consistent performance and consistent structural properties throughout a size range of bikes. But now we literally size every tube of the bike proportional to the size of the frame. And sometimes more than that, sometimes even wheel sizes and things are proportional to the size of the frame. But by sizing that tube, it might look the same. The general shape and design might be the same. It's just a little bit smaller or a little bit bigger for each frame size. And that means the 100-pound rider on the smallest frame has the same kind of ride quality and feel and response as the 250-pound rider on the largest frame. And that's the goal there. In addition to that, the carbon fiber layup itself, we can put more or less layers of carbon fiber in a given tube or tube junction to make the frame lighter or to add material to make it stiffer. So we can tune it. The bonding design and techniques, we've actually, since Kestrel started, we've done bonding. We use aerospace grade structural adhesives. This is not so much a point for this audience. Some of the competitors use, some of our competitors use cheaper spec materials like a 1-part epoxy. We use a 2-part epoxy. They actually have to squirt it out in production and mix it up. But that's what gets the best results. It has the higher strength, the higher shear strength, and it gives you the better quality end product. The other thing that all our frames that are going to have, the ride tune stays and our EMS fork technology. So like I said, we introduced the carbon fork to the world in 1989. And what we do now is every model of bike has its own specific design fork. So if you look at the image here, you can see the main frame in blue, and then you see the rear stays in the silver or gray, as well as the fork. So what we're able to do these days is to match the performance and match the quality and design of the front end to the rear end, so you get a very balanced ride and a very balanced feeling, kind of a repeatable performance out of the frame. No compromise geometry and fit. That's just something we do because even though we're carbon fiber engineer guys, we're a bicycle company first, and so what we try to do is not cut corners to make one size fits all frames. It seems a silly thing to do in carbon because carbon's so light. If there's no reason to make a tube a little bit shorter to make a frame a little bit lighter. Get the geometry right, fit the rider correctly, and design to that just as you would to weight or stiffness. Let me grab a little sip here. This picture is to remind me that so kind of basics of what we do, and now this is we have a couple frames. Can't put my hand there. A couple frames that I'll show you some images of, some examples of the actual design process that we go through. One of them is this RT700, which is our brand new road bike. We have a couple of them up here you can check out after. And then the other one is our real tri-race specific bike. It's called the Airfoil Pro. It's very specific to triathlon racing. It's not legal actually for any road racing or time trial use, but it's a very fast bike. So I think I've covered most of these points. We do all the design, all the engineering is done in our Santa Cruz offices. The frames are made overseas, like just about everybody is these days. We used to have the factory in Santa Cruz, so we have unlike most bike companies that go overseas to get carbon, we actually have experience and the engineers who have set up factories in not only in the U.S. but in other countries as well. So we can go to those factories and we kind of know how to lay up bikes, and we know how to do the finishing work and all. In fact, from the president of our company, who has set up carbon bike manufacturing factories around the world and on down. The carbon, I talked a little bit, but just to reinforce that the carbon's infinitely tunable. So it comes in very thin sheets, and what we do, I don't think I really show this. I don't really have the manufacturing so much as the design stages here. So what you can do with the carbon, it's usually what we call unidirectional carbon. So the carbon's all going in one direction on the sheet, and then the sheets are cut to the different angles that we need, and we use different thicknesses of sheets that we need, and then we stack those sheets. So say, oh, we need 6 layers in this big tube, or we need 5 layers in this smaller tube, or what have you. The different number of layers, the angles, the thicknesses along the tube or at the junctions, all that's tailored to the particular design. Everything we do now is 3D solid model CAD. Didn't used to be when I started at Kestrel. It was drawing centerline drawings by hand and working with industrial designers and actually drawing this stuff, drawing it on paper. And then the interesting thing when we got into real 3D modeling is that the software is really capable now, but about 10, 12 years ago when we were first starting to do it seriously, even say we use Pro Engineer software, and we had designs that those guys couldn't model, so we actually had to have customized software made to be able to model the crazy compound curves and shapes that we were doing. But this is how the design cycle starts out. We actually work with some very good industrial design firms, usually local to the Santa Cruz area, and we give them some definitions on what we're looking for in a bike, and start bouncing ideas around and getting some sketches going. This is the Airfoil Pro tri-bike that I showed you. Once that basic concept's done, then we start getting into the details. Okay, how is the cable routing going to work? What's the seat binder going to look like? And so they'll get into these multiple iterations of these types of sketches. This one looks to be pretty far along in the process in terms of the hand sketches. And sometimes by the way, sometimes they use computers for their conceptual stuff or sketch type stuff. This is a little cable port that came out of probably a dozen concepts. It's the one we kind of zeroed in on the RT700 bike. Once we have those concepts done, we'll start doing the solid model CAD drawings. This one, I like this shot because it's, this is Airfoil Pro. But what it shows is the solid part there is the main frame, so that the main frame design was pretty much done at that stage. And so now they're building the rear end onto the bike. All the clearances, they're laying out all the clearances and trying to put in the hard points, like the rear dropouts where the wheel bolts in and where the brake bolts in. And then a little further on, same frame. This is a cool shot because you can actually see those green and gray lines that are going down the main big tube on the screen there, the down tube, is actually some of the cable routing. So they're able to put in the anticipated thickness of the carbon fiber wall and simulate the cable routing through the frame, make sure there's no interferences. A little hard to tell, but these metal, you can see some of the little metal pieces that are bolted or riveted onto the frame that guide the cables and things. So they're actually able to put those into the CAD model and make sure everything's good, functions properly before we go to machining, CNC machining a very expensive mold. And by the way, all this stuff we do, if we make 5 or 6 sizes of a frame, it has to be done for all the sizes. Here you can see this is the RT700 model, and obviously this is a fairly finished model, but you can see some of those concept sketch pieces, like the little gold cable guides, where they're actually fitting them into place and designing the frame to be molded to accept them. Another one, that under the bottom bracket cable guide piece, this is a little injection molded thermoplastic piece, and it went from that, I think, 3-piece concept sketch down to this. So basically, there's little the little ports. I guess I might have. I don't know if you guys can see let's see my pointer here. So this port area is actually a hole through the frame, and the cables come out. And then you can route them through the plastic piece. Lost my marker again. There it is. And then it goes into these holes here to go up to the front derailleur and rear derailleur. This shot here, I'm not sure what this shot's for. I just think it looked really cool, so I put it in there. It reminded me of like Terminator 2, Liquid Man. But it was the rear drop route of the RT700. This is a problem. We have a little power problem up here, I guess. I should have turned my lighting down more. And then actually a big part of it is checking all the clearances. So we actually get I think they're IGES files from Shimano or whoever, and actually put the components in and check all the fit and clearances. I'm gonna run out of power. Although, it might be pretty done anyway. And then we can do finite element, using that CAD model, we can do some finite element analysis depending on what the frame is and what the needs are. This bike doesn't have a seat tube, so it's kind of nice to put some loads into it. You can do the whole frame or you can do sections. Sections are usually the better way to go. Another thing we can do with the CAD model is before we commit to tens or hundreds of thousands of dollars worth of machined metal molds, this is actually a CNC machined piece of foam, actually several pieces of foam. So they actually machined a frame out of solid foam, assemble it together. We check it out. Typically, we change it. We did change some design details on this. That used to be really, there you go, thanks. Excellent. I can turn my lighting up here a little. That used to be really expensive stuff to do, and it's just, the prices on getting that stuff is going down like mad these days. And in fact, this piece is actually done in-house by the industrial design firm we work with. And then boom, you've got prototype. Once you check everything out, you make the mold, we go to the prototyping phase. And this is probably the first or second mainframe of the RT700. You can see, my cursor shows up, you can see the little port here. So that's actually the little metal port, and that's actually a stereolithography prototype part as well. I don't know why my cursor disappears. Back here you can see these little tabs sticking out in the back. That's where the stays in the rear end is going to bond on. How's the time? JD, how's the time? Okay, thanks. Another little prototype, not the prettiest picture, but I mean, this is raw right out of the mold. There it is. So this is an SLA part or stereolithography part. I don't know if you guys are familiar with how that works, but that's basically where they have a plastic solution and they cross lasers to solidify it and build this piece. Not out of thin air, but out of thin plastic, fluid plastic. So they call it SLA, stereolithography. I don't know what the A stands for. Maybe it's a Canadian process. I'm not sure. Stereolithography, eh? And then you saw the mainframe. This is a bonding fixture. Part of the prototyping is figuring out the tooling and just proofing it all out. So This is actually, the bonding fixture is quite large to hold the whole frame and bond everything into alignment at one time. And the nice thing about carbon is it can't be bent or deformed. So once it's bonded in alignment in the fixture, it's in alignment for life. But that means you better do it right the first time. So that's actually where the stays and the dropouts are being bonded into the main frame on this fixture. Not real fancy stuff, but it's effective. And it's made for production speed. Finally, once the basic prototyping is done, we do a whole battery of structural testing. I think, at Kestrel, we pride ourselves on having really stringent test requirements. I know PI was concerned with that on carbon fiber products, and we actually agree. So the testing that we do is the kind of stuff that was done on 1970s era's heavy-duty steel bikes and 10-speed type frames. And so we surpass all the different government requirements, whether it's US or Europe or Japan. Our tests meet or beat all of those. In this case, this frame is actually, of course, the test machine is kind of vertically oriented, so it's actually pushing the frame down to simulate a load at the front wheel axle. And just it's like a frontal impact load. It'll take 1,000, well, probably say 800 pounds and up to cause any kind of structural damage to the frame in that way. On some bikes, particularly the tri or the aero bikes, we also do wind tunnel testing from time to time. This is that Airfoil Pro that we saw some of the development images, and it's being set up at the low-speed wind tunnel down in San Diego. Here it is with this is our top pro triathlete. His name's Chris McCormick. He's actually quite a good triathlete. He won about 3 or 4 Triathlete of the Year honors for his 2006 accomplishments. And one thing we did in 2006 was get him off his more conventional seat-tubed bike onto this no seat-tube super aero Airfoil Pro bike. And what we found is that just the frame and fork, what we call frame set, the frame and fork alone, saved him about 100 grams of drag at 30 miles an hour, which is basically if you rode 25 miles or 40K in 1 hour, it would knock a minute off of that time, just the drag savings there. The other thing is that this bike is designed to put you in a very aerodynamic position, and the position change knocked another 100 grams of drag, so another minute. So say he can go way more than 25 miles in an hour, but say I was going 25 miles in a 1 hour ride, now it would take me 58 minutes. So it's a huge, aerodynamics in triathlon and in pro cycling, especially the time trial stages that I'm sure all of you folks have seen on TV and the internet. It's the time trials are a pretty big catchword these days. It's exciting to watch, and the bikes are crazy and expensive. So it really is important what you do aerodynamically. The result, he was the winner. He was the best triathlete in the world in 2006. He won, I think, all but 2 races that he entered. He got second place in those 2, and he really proved that what we showed in our development and our wind tunnel testing worked. Ironman Hawaii, the big race of the year, he got second. It was I think he was like 1 minute and 11 seconds behind the guy who won. So I think the 3rd closest finish in Ironman history. So we're looking for him to win the race this year. But definitely what we did in the wind tunnel and his positioning has helped him move up from 6th place a couple years ago, 2nd place last year, and breathing right down the neck to take 1st this year. And that is the presentation. We have a few minutes open for questions you folks may have, and feel free to check out the bikes as well. Yes?
You mentioned this at the beginning. How many frames do you produce in a year?
How many frames do we produce in a year? It's actually kind of confidential information. So we're a small company, and you know, we make bikes. Now this year we make the bikes from $1,999 and up. But it is you know, we're very much a specialty manufacturer, so it's really competitive, that information. But we make in the range of like a few thousand frames and bikes a year, not tens of thousands. Yes.
So carbon is much stronger than the traditional metals. How come you don't see it in mountain bikes?
I'm sorry. Why don't we see mountain bikes?
Yeah.
Did you say?
The carbon frame mountain bikes are few and far between.
Yeah. Well, I think the question is why, if carbon is such a strong, good material, why don't we see more mountain bikes? And I think the simple question is you are going to see them. More companies are using carbon for mountain bikes now, and more companies that we're aware of are heading that way. So if I talk to a company that just makes mountain bikes, I say, dude, you got to go carbon. You know, if you don't do it, somebody else is going to beat you to it. So it's actually a great material for mountain bikes, but just like in road bikes, where it took a while for it to gain acceptance, it's the same thing in mountain bikes, and then even more so because people are worried about, you know, people crash all the time, or they're worried about rocks and things kicking up and hitting the frame. We have made carbon mountain bikes since 1988, and I can tell you, they're pretty bomber. You know, I mean, I'd say we tend to make them a little heavier and a little thicker and tougher, but they've been very successful over the years. But it is more of that acceptance thing. Another thing is that with full suspension, when full suspension became really prevalent, some of the benefits of the ride quality of carbon aren't as noticeable, and because you've got big fat soft tires and you've got suspension, so you want it to be super stiff structure because the suspension's giving you the comfort, and you don't want it to be too expensive. So carbon fiber, the price is working down, the design, you know, the whole thing is coming that way. And I think just like if you watch the Tour de France now and there's virtually no bikes that are made of metal in there, whereas 10 years ago, most of them were metal, and 20 years ago, all of them were metal. I think you'll see that in mountain bikes. Yes?
What is the disadvantage of not having the seat tube, other than that that is not legal for UCI races and stuff?
Right, but what's the disadvantage of, like, why don't all bikes not have seat tubes? Well, you're right. I mean, the biggest issue is UCI/USCF regulations, you know, racing regulations. The bike pretty much has to have a seat tube to be legal. As a result, I mean, that really limits what we can do design-wise, because we can make the triathlon bike specifically for, and not care if it's UCI legal. So we can do that and make it, I wouldn't say target it to that audience, but actually make it for that audience, make those people as fast as they can be. But on a road bike or a bike for the general population, it's just the marketing of that and what's accepted and what people are looking for. It becomes very complex to go against that. It makes a great ride. I can tell you, if you have a road bike and it's designed properly without a seat tube, like that one of those first slides I showed you, it's in a phenomenally riding bike. You know, it's actually, at the time that 500 series frames were made, it was actually the stiffest frame that we made in the bottom bracket, but also the smoothest riding bike. So, you know, we have to go with what the market wants, and definitely the UCI rules do play into that. In terms of the structural part, there is, that frame also had aerodynamics built into it, the aerodynamic tube shape. So whenever you go for those kind of things, you're going to lose a little bit on the structural efficiency. So I would say if you want to make the absolute lightest, stiffest frame, you're going to generally want a triangulated frame. But the frame I showed you there, that weighed 2.9 pounds in 1992, 1994. So you could get really close to 2 pounds, just like the triangulated frames are now. Thanks. Yes?
So let's say you have a carbon frame. At what point do you look at the frame and say, oh, I have this nick or this gouge or X kind of damage, and say, oh, I need to get a new one?
Right. His question had to do with basically how do you tell if there's any damage to the carbon frame? How do you know, and how do you know if it's bad enough to be a concern? And that's another thing. 20 years ago when Kestrel started, it was this whole learning curve on all that. I mean, we felt we were teaching the industry, the bike shops, the consumers about carbon fiber in general. But I think that, and then over time, obviously, we and then more and more people manufacturers have used it, so it's come to be accepted, and people have learned how to identify those things. I would say that damage tolerance in a bike frame is very dependent on the weight of the frame, not so much the material of the frame. So anytime you're pushing the weight way down, the way to make a bike frame light is to make the wall thin. And so when you start doing that, it's going to become less damage tolerant no matter what you do. So with carbon, I've actually seen, we've actually seen things where in say a criterium race, and people have gone down, and five guys crash in a pileup. They get up, 3 of them have a steel or aluminum frame that's bent, and they can't keep riding, but the guy on the Kestrel or the carbon frame could. So what I see in carbon is when it gets kind of generally slammed, it's really good because it doesn't bend. But it is different than metal for localized impact, especially sharp stuff, is not so much the big stuff, because metal tubes dent too. So they're damaged by the same kind of things, but the damage is different. So I guess to answer your question is, usually you need to you take it to the bike shop that's qualified to look at it, and or send it to the manufacturer. We'll get people, oh, I crashed, and they'll send us a digital photo of some damage where the handlebar came around and smacked the tube or something. Start from there. I think that's about all the time we have. So thanks a lot for coming and for the opportunity.